Hello again. In this topic, we're going to introduce a couple of theoretical results that are important for later results in the course. They're called Rolle's theorem and the mean value theorem for derivatives. And basically what they are situations that, while it may not seem too important to us if we're just focused on the technical things, how to use the derivatives and how to calculate things. Without these theorems, much of the later processes that we're going to use, we wouldn't be guaranteed that they work. So, if you're going into engineering, if you're going into the sciences, you're probably not going to need these topics much past this course. If you're going into mathematics, you're going to have to take an advanced calculus course, and you'll see this again, and you'll really delve into why this is important. But I'm going to just ask you to learn a little bit about the theory here. So first this is Rolle's theorem. Here's what it says. If a function is continuous on a closed interval and differentiable on the open interval AV, and f of a equals f of b, then. I'm leaving this blank because I want to help you think about this. Let's picture this situation. We have a continuous differentiable function, and f of a is equal to f of b. Let's think about it. So that means that we have some a value here and some b value here. But f of a equals f of b. What that means is that at both of those inputs, the height, the level, is the same. Right? So let's say there's the point A, f of a, and here's the point B, f of b. But for Rolle's theorem, that level, right, that level has to be the same. Right? There's that level, poorly drawn. F of a equals f of b. So now if we think about this, if we were to try to draw a curve between those 2 points, if we were to draw a curve between those 2 points, it's got to be continuous, it's got to be differentiable. What must be true about that curve between those 2 points? Think about it. Maybe draw a curve or two. See what happens. See if you can find any things that are comparable between any of the curves that you draw. Here, I'm going to draw a curve. Here's a curve I'm drawing in green. Maybe it looks like that. There's a curve in green. Let me draw a different curve. Here's a second curve in orange. And maybe it does something like this. Here's a curve in red. And this curve is just going to be the constant that connects, the line segment, the constant line segment that connects those 2 points. What's true about all 3 of those curves? I'm going to highlight some points here. I'm going to highlight a point here. I'm going to highlight this point up here on the green curve. I'm going to highlight these points, there's 3 of them, on the orange curve, and I could highlight the entire red curve. What's true about all those points I just highlighted? For all of those points, what's the value of the derivative? 0. If f is continuous on an interval and differentiable on the open interval, and f of a equals b, f of a equals f of b, then there exists c on the interval a to b, the open interval a to b, such that f prime of c is 0. So what this is saying is, if we know that the endpoints have the same level, then somewhere over the interval the derivative must be 0. There must be a stationary point. There must be a critical point. Okay? This is only valid if the function is continuous and differentiable over the interval. It's an important result. We're going to see why that's important later on. So now let's consider this situation. Now I guess I should mention, let's go back here for a second. I should mention, this is what's called an existence theorem. It tells us that the C exists. It doesn't tell us how to find it, and it doesn't tell us if there are multiple C's. Right? For the curve in green, there was only one value of C that worked. But the curve that I drew in orange, there were 3 C values that worked. The curve that I drew in red, the line segment, the constant, the derivative is always 0 at the constant. And so there were an infinite number of C values. It's an existence theorem. It tells us that there are C that exists. It doesn't tell us how to find it. It doesn't tell us how many. Consider this situation. Here we have the function x squared plus x minus 2 on the interval -3 to 2. Let's note that f of -3, that would be 9 plus -3, that's 6 minus 2, that's 4. And f of 2 is 2 squared, that's 4 plus 2 minus 2, f of 2 is 4. So note that f of -3 is 4 and f of 2 is 4. And f is continuous on -3 to 2 and differentiable on the open interval -3 to 2. So, by Rolle's theorem, there exists C on the interval -3 to 2 such that f prime at C must equal 0. That's what we know. Now again, it doesn't tell us what the C is. In this case, it's relatively easy to find the C value. F prime of C, so if f prime of x would be 2x plus 1, right? F prime of x is 2x plus 1. So then we would have 2c plus 1 is 0. C is -1/2. But the Rolle's theorem guarantees that there is a C value on the interval such that f prime of C is 0. Alright, so why don't you try the next one? Let's look at that situation. What if the function is 1 over x squared minus 6x plus 9 on the interval 2 to 4? Does Rolle's theorem apply? Why or why not? And if it does, find the C value. Alright, so let's take a look at this. If f of x is 1 over x squared minus 6x plus 9 on that interval 2 to 4, you might say, okay, well, let's see. What's f of 2? F of 2, that would be 2 minus 12 plus 9. That's -1? No, 2 squared is 4. 4 plus 9 is 13. 13 minus 12 is 1, so that's 1 over 1. That's 1, okay. F of 2 is 1. F of 4, that's 16. 16 minus 24 is -8 plus 9. That's also 1 over 1, which is 1. So that's looking good. Okay, wait a second. What about continuity? See, it's a little tricky here. Notice that I could rewrite this function, f of x. Notice that x squared minus 6x plus 9, that's the same as x minus 3 squared. So f has a discontinuity at x equals 3. Rolle's theorem does not apply. The function is not continuous over the given interval 2 to 4. So even though f of 2 equals f of 4, there is no guarantee that there is some c on the interval such that f prime of c equals 0. And in fact, in this case, there isn't one. Okay, so Rolle's theorem does not apply. We cannot guarantee some c on the interval 2 to 4 such that f prime of c equals 0. Let's lead up to another situation now. Let's think about this problem. On a stretch of road, there are lines painted every quarter mile. Law enforcement observes a car that takes 12 seconds to complete 1 quarter-mile segment. If the speed limit on that road is 70 miles per hour, should the driver be cited for speeding? All right, so I'd like for you to think about this problem a little bit. Maybe try a little work on your own before I do it. So now would be a good time to pause. All right, so let's be careful about units here. We are told that we have the speed limit is 70 miles per hour, but we have a time in 12 seconds. So let's think about this a little bit. Notice that 12 seconds, and let's multiply that by the unit conversion factor. I know that 1 hour is 3,600 seconds. And so that would be 12 over 3,600 hours. All right, now let's think about this a little bit more. Let's think about an initial position and a final position. Here's what I know. Let's think about the position function. Positions. I know that s of 0, if we think of s as the position function, let's say that s of 0 was 0. That was the first line, the starting line. And s of 12 over 3,600 hours, right, would be 0.25 miles. Right, so seconds, miles, not seconds, hours. Hours, not seconds. Sorry about that. This is in hours, miles, hours, miles. So here's what I know. If we think about these 2 points, then right, I have a starting point and I have a final point. What I now know is then that the average velocity would be equal to s of 12 over 3,600 minus s of 0 over 12 over 3,600 minus 0. So that would be 0.25 minus 0 over 12 over 3,600 minus 0. Now I'm going to have to use a calculator here. Let's see. 0.25, and let's divide that by 12 over 3,600. If we use parentheses correctly, this ends up being 75 miles per hour. So I know that the average speed for that vehicle was 75 miles per hour. So if the average speed is 75 miles per hour, it should seem reasonable that at some point over the time interval 0 to 12 seconds, at some point over that 0 to 12 seconds, the instantaneous velocity should have also been 75 miles per hour. Should that driver be cited for speeding? Yes. Under reasonable circumstances, under reasonable assumptions, since the average velocity was 75 miles per hour, then at some time on 0 to 12 seconds, the instantaneous velocity must have also been 75 miles per hour. Doesn't say it was always 75 miles per hour. It could have been under that for some point. It could have been over that for some point. However, at some time during that interval, the instantaneous velocity was 75 miles per hour, and so then, should the driver be cited for speeding? Well, yes, the driver could be cited for speeding. This is actually an application of what's called the mean value theorem for derivatives. And it starts off similarly as Rolle's theorem. It says if the function is continuous on a closed interval and differentiable on the open interval, but there's no restrictions on the values of f of a and f of b. So let's just arbitrarily, there's a and there's b, and I'll just say, here's the point a f of a, and here's the point a f of b. I'm sorry, b f of b. So there's a. So now, if we were to draw a curve over that, I don't know, maybe there's that curve. Here's what the mean value theorem says. It says basically, think of the average value. All right, so the average value would be the slope of the secant line of the curve over those points. So let's think of that slope. So here's the average value. And this is going to be tough for me to draw, but it looks maybe something like that. There's that average value. What the mean value theorem says is that there is some c on the interval a to b where the slope of the tangent, where f prime of c has the same value as the slope of that average value, the slope of the secant. And so maybe it's, I don't know, maybe about right here. Maybe there's a c value such that the slope, again, this is tough for me to draw freehand, that slope is the same. So here's that c value on the interval. All right, so the mean value theorem says if f is continuous on a closed interval, differentiable on the open interval a comma b, then there exists c on the open interval a b such that f prime at c is equal to f of b minus f of a over b minus a, such that the instantaneous rate of change is equal to the average rate of change. Right? Instantaneous is equal to the average rate of change. This is the mean value theorem for derivatives. And this is actually a very important theorem in building some of the topics we'll see later on. I'm going to use the mean value theorem to prove something in the next topic. So let's see an example. Let's consider the function 5x squared minus 6x plus 8 on 0, 5. Let's note that this is continuous and differentiable. And so the mean value theorem, states there exists some c on the interval 0 to 5 such that f prime at c would equal f of 5 minus f of 0 over 5 minus 0. That's what it says. Now it doesn't say how to find the c, it just says that there's a c that exists on 0 to 5 such that this is true. Now we can actually find it. It's not that difficult. The arithmetic in the calculus isn't too difficult here. F prime of c, the derivative would be 10x minus 6, so 10c minus 6. Let's see, f of 5, that would be 5 times, let's see, so 5 times 25 minus 6 times 5 plus 8. That would be 103. F of 0 is 8 over 5 minus 0 is 5. So 10c minus 6 is 103 minus 8 divided by 5 is 19. And this is, beginning algebra now at this point. Add 6 is 25. C is 25 divided by 10. C is 2.5. So when C is 2.5, the slope of the curve at that point should be equal to the average value, the average rate of change, I should say, the average rate of change of the function over that interval. Now this is difficult to visualize for this function, but it is in fact valid. Alright, so now, again, I've been mentioning, why is this important? This is mostly sort of theoretical, but let's actually use one of these theorems to make a little proof. So again, these theorems, they help build other results that are necessary for the structure of calculus that we're going to be using from now on. For example, back in our rules for derivatives, we learned that if a function was constant, right, the derivative was 0, right? We learned that d by dx of a constant was 0. Now, an important question, is the inverse true? If the derivative of a function is 0 for all x in an interval, then is the function necessarily a constant over that interval? Let's see a brief proof for that. Alright, so let's start with what we know. We know the function has a derivative equal to 0 for all x in some interval a, b. Alright, so since the function, since f is differentiable, then f must be continuous. On the interval AB. Alright, so it's differentiable for all x in an interval. Differentiability implies continuity, not the other way around. If a function is differentiable, we know it must have been continuous. Alright, so now I will let x1 and x2 be on the interval, exist on the interval a, b, and arbitrarily let's let x1 be less than x2. That that doesn't matter too much. I could have changed that around, but we're just going to let x1 be less than x2. Then f is continuous and differentiable on the interval x1, the closed interval x1, x2. So now I'm saying, okay, let's just choose a couple values that are within my given interval. Call them x1 and x2. They could be any numbers on that interval. The function is continuous and differentiable on x1, x2. So, by the mean value theorem, there exists C on the interval x1, the open interval x1 to x2, such that f prime at C must be equal to f of x2 minus f of x1 over x2 minus x1. Now, if C is on the interval x1, x2, but that interval is within a to b, we know that f prime at C must equal 0, because we were told that f prime of x is 0 for all x in the interval. So f prime at C must equal 0. So f of x2 minus f of x1 over x2 minus x1 must equal 0. Alright, well now I know x2 minus x1 is not going to equal 0 because I said earlier that let's let x2 be less than x1, or x1 less than x2, so they can't be equal, so the denominator cannot equal 0. So if f of x2 minus f of x1 over x2 minus x1 equals 0, then f of x2 minus f of x1 must equal 0. Then f of x2 must equal f of x1. I say, okay, well that's nice. They're the same value. But remember that x2, since x1 and x2 were arbitrary values, on the interval AB, then what that means is for any of those x1, x2 that we choose, their function values are the same. And if the function values are all the same, that means that the function must be constant. Since x1 and x2 were arbitrary values on AB, and f of x1 is equal to f of x2, then f is constant on the interval a to b. So that tells us that we just proved that if a function, if the derivative of a function is 0, then the original function must be a constant. Seems obvious. Here's proof that it's true, right? Just because something seems obvious in math doesn't mean it's necessarily true until it can be proven true. That's the big idea of mathematics. Find something that seems like it's true. Find a pattern. Then figure out how to prove it's true. That's the real mathematics. Alright, so that concludes what we need from this section. In our next topic, I'm going to use the mean value theorem again to prove something, so you might want to kind of review this proof in preparation for the one we'll see in the next topic. All right, have a great day. See you next time.